Oh no, not the machines. Hello, welcome to eProm Toast. Today I have something a little more informal and fun. Everyone's been talking about it, it's in the news, it's winning art. We're going to be playing with AI today, specifically ChatGPT. Now, what should we ask it first? Figured, you know what? Might as well test it out. So it says 16-bit register in assembly language is a type of data storing location that can hold value with a size of 16 bits, which is equivalent to 2 bytes or 4 hexadecimal digits. Registers are used to store temporary data during program execution and are directly accessible by the CPU. In assembly language, registers are typically identified by names such as AX, BX, CX, DX, so on. For example, in the x86 architecture, the AX register is a 16-bit register that can be used for arithmetic and data manipulation operations. It can be divided into two 8-bit registers, namely AH, high byte, and AL, low byte, which can be used to access the upper and lower 8 bits of the register respectively. In general, the use of registers in assembly language can result in faster and more efficient code execution because data can be accessed quickly without the need for additional memory access. Okay, now let's see. Show me hello world in x86 assembly. Okay. We're going to let it finish. Certainly, here's an example of a Hello World program in x86 assembly language for 32-bit Intel architecture on Linux. So you got section data section used to declare constants and variables, message DB define byte, hello world, 0 define a null terminating string, section text, text section used to write code, global start, entry point for the program, start label for the entry point, write message to the standard output using the write system call. Move EAX, so this is a 32-bit register. It would be R on a 64-bit. System call for write. Move EBX 1. File descriptor for stdout. Move ECX message, address a message string. Move EDX 13 number of bytes to write, excluding null terminator. Int integer 0x80 interrupt to invoke the system call. I've seen this before, so I'm guessing this is the interrupt command, not integer interrupt. Interesting. Exit the program using the exit system call. Move EAX1 system call for exit. XOR EBX return value of 0. Interrupt 0x80. The program defines a string of hello world in the data section and uses the move instruction to set up the parameters for the write system call to print message to the standard output. Then uses another move instruction to set up the parameters for the exit system call to terminate the program. And then here's where you assemble it in Linux: nasm-f, elf32, hello world.asm, ld-m, it's an argument, elf5386-s-o, hello world.o, link the object file to create /hello world to run the program. When you run the program, you should see the hello world message printed to the terminal. Let's try something a little more complex. Show me an Ohm's law calculator in x86 assembly using 64 registers. I want to see what it'll output. Now we're just going to wait for it to finish. Wow, that's a lot of assembly. Certainly, here's an example of an Ohm's law calculator program written in x86 assembly language for 64-bit Intel architecture on Linux. Section data, of course. Data section used to declare constants and variables. Prompt, define byte. Enter the number excuse me. Enter the voltage in volts. Prompt to define byte. Enter the resistance in ohms. Result _FMT, define byte. The current is %.2F amps 10,0. Section.bss. BSS section used to declare uninitialized variables. Voltage request. I'm not familiar with this command. 1. Reserve 8 bytes of space for the voltage variable. Resistance. Resc1. Reserve 8 bytes of space for the resistance variable. Current Resc1. Reverse 8 bytes of space for the current variable. Section text. Text section used to write code. Global start, as we've seen before. Entry point for the program. Start. Label for entry point. Prompt the user for the voltage. Move RAX4. System call for write. Move RBX1. File descriptor for stdout. Move RCX prompt. Address to the prompt string. Move RDX31. Number of bytes to write, excluding null terminator. Syscall. Invoke the system call. Read the voltage from standard input. Move RAX0. System call for read. Move RBX0. File descriptor for stdin. Move RCX. Voltage. Address to the voltage variable. Move RDX8. Number of bytes to read. Syscall. Invoke the system call. Prompt the user for resistance. Move RAX4, system call for write, move RBX1, file descriptor for stdout, move RCX, prompt 2, address of the prompt to string, move RDX 35, number of bytes to write, excluding null terminator, syscall, obviously invoke the system call. Read the resistance from the standard input, move RAX 0, system call for read, move RPX 0, file descriptor for stdin, move RCX, resistance, address of the resistance variable, move RDX 8, number of bytes to read, syscall, invoke the system call. Interesting. Calculate the current using Ohm's law. I equals V divided by R, where V equals I times R. Either way is fine, depending on what operations you're doing. Move RAX, voltage, load the voltage into the RAX register. Move RBX, resistance, load the resistance into the RBX register. File keyword RAX, load the voltage into the FPU stack. Filed FILD keyword. Oh, I read this one already. Alright. FDiv, divide the voltage by the resistance. FSTP keyword current, store the result in the current variable. Here we have display the result to user. Move RAX1, system call for write, move RBX1, file descriptor for stdout, move RCX, result underscore FMT, address of the number, address of the result format string. Move RDX23, number of bytes to write, excluding null terminator, syscall, invoke the system call. Exit the program using the system call, move RAX60, system call for exit, XOR RDI, RDI, return the value 0, syscall, invoke the system call. Interesting. So, this was supposed to be a quick video, nothing too much. AI is definitely a lot better at coding than I am, and I give it props, because this is actually a really useful tool. I sort of just wanted to play with this a little. My video from yesterday was pretty long, like 40 minutes. So I wanted to do something a little less involved and fun. And we'll be making quite a lot of use of this resource later on this channel. Well, we're over time, so have a good day, and remember, Big Brother is always watching.